Hello everyone, today in this video we are going to talk about some basic concept related with current. So let's start the video. So this is the conductor and this is the range of resistivity. So resistivity of conductor will go from 10 to the power minus 8 to 10 to the power minus 6. So basically we are talking about the metals. And semiconductors like silicon and gallium, they have the resistivity range 10 to the power minus 6 to 10 to the power 4, and insulator they have more than 10 to the power 4. So just in order to remember this, we'll write from minus 8 to 8. So from minus 8 to minus 6 is conductor, and starting from minus 6 to 4, that is minus 6 to plus 4 is the semiconductor, and above 4 is the insulator. So this is the thing. So 8 to 6 4, just you have to remember this number 8 6 4 in the reversed order. So conductance. So this conductance is the opposite of resistance. So resistance will try to oppose the current, and conductance will allow the current, and this is just a reciprocal of resistance. So G is equal to 1 by R, and SI unit is ohm inverse, and we can write MHO also, ohm inverse, or Siemens S. And conductivity, which is the reciprocal of resistivity, and conductivity is 1 by resistivity, and sigma is 1 by rho, and again the unit of resistivity was ohm meter. Now this is per ohm per meter, or MHO per meter, or Siemens per meter is the conductivity. So let's current density, as we have seen in the previous video. So current density, it is the current flowing per unit area, but the area has to be normal to the flow of current. So current density is a vector, so the formula is current density is current by area. Basically it's a current flowing per unit area, but area has to be held normal to the surface. Area has to be kept normal to the flow of current. So SI unit is ampere per meter square. So from here we can see ampere per meter square. So this is, so see, current is flowing and the area is kept normal to the flow of current. So for this I can write, but if the area is not perpendicular, so as you can see area vector is going down and current is flowing in this direction. So for this case the formula used will be current by component of area. So I forgot to write, please write this, component of area in the direction of current. So component in the direction of current is A cos theta, as this is the angle, so this will be A cos theta, area times cos theta. So this component is the direction of current. So I can write now J is equal to I by E cos theta. So if you take this side, so I will be JA cos theta. So if you see something as cos theta, then this will be dot product. So as you can see, so this is scalar, that's why it is a dot product. So that means J has to be a vector. So current density is a vector. Okay, so this is all about current density. Now mobility. So mobility means drift velocity per unit electric field. So on applying the electric field, electrons start drifting in one direction. So how much velocity they gain when electric field is applied, that is the mobility of the charge. So mobility means how free they are inside the conductor. So unit of mobility is, now you can see this meter per second, and electric field is Newton per coulomb. So if I multiply this with meter and meter, so this will be a meter square per second, and this is Newton meter. So this has come this side, Newton meter per coulomb. So Newton meter per coulomb, that is work done by charge, is the potential. So this will be meter square per volt per second is the another unit of mobility. Just you can memorize this if you don't want to do this line, or you can, if you want to understand, you can go. So just multiplying with meter and meter to make this as potential, that is volt. So let's derive the relationship between current density, that is J, conductivity, that is sigma, and electric field E. So the formula for drift velocity is Vd is equal to minus EE tau by m, and now I'm writing it in vector form, that's why the minus is there. So again, relationship between current and drift velocity is given by this. Okay, and definition, from definition I can write current density is I by A. So I'm not writing this in a vector form right now, so this is E by E. So let's put the value. So for Vd, current, I'm putting this one, I'm putting the value of current, and area I'm cancelling it. So if I want to write this in vector form, now the velocity and the current are in opposite direction. So the electron flow is in one direction, but the direction of current will be in opposite direction. So in vector form I have to write negative. So J is equal to minus NE Vd. So for electron, Vd and I are in opposite direction, that's why I'm writing the minus sign. So now I'll use equation 1, and so I'm just putting the value of Vd. So we get this, so I'll multiply this. So this is the current density, Ne square E tau by m. So now this thing I'll take outside, and this is, I'm keeping in one bracket. So but this is, this whatever things is there inside the bracket is reciprocal of resistivity. We know resistivity is Ne square tau, so 1 by resistivity will be this. So this formula I can write this as current density is E time 1 by tau. So but we also know this is 1 by resistivity is conductivity. So this is the conductivity. So instead of this I'll write conductivity. So current density is electric field times conductivity. And you can try deriving Ohm's law in vector form, which is there in the book. So try this. So now next is temperature dependency of resistivity. So as we all know, resistance depends on temperature, as resistivity also depends on temperature. Resistivity is independent of shape and size of a conductor, but it depends on temperature. And it was found that if ρ0 is the resistivity of a material at temperature T0, suppose ρ0 is a resistivity at temperature T0, then its resistivity at temperature T is given by this formula. So resistivity at temperature T is equal to resistivity at temperature T0 bracket 1 plus alpha T minus T0. This is experimentally found relation, so we don't need to derive it. So where alpha is a constant called temperature coefficient of resistivity, this alpha is a constant and we call it temperature coefficient of the resistivity. And if you want to define this, we just need to take alpha this side. So if you rearrange the equation, you will get this will go this side, this temperature will go this side. Try this step by yourself. So you will get alpha is equal to, so this is resistivity at temperature T minus resistivity at temperature T0. So this is basically change in resistivity, and this is the original resistivity, and this is final time minus initial time. This is also change in temperature. So this coefficient of resistivity can be defined as increase in resistivity. This is the increase in resistivity per unit resistivity. So this is the original resistivity, and per degree change in temperature. So this is the definition for temperature coefficient of resistivity. And similarly we can do same for resistance. So if R0 is the resistance as at T0, so resistance at temperature T can be written in this form. And if you change T minus T0 by delta T, and that time you can write RT is equal to R0 1 minus alpha. So instead of T minus T0 I am writing delta T. So this is the formula. So you can try some questions from the book. So this is a very important formula, and I have seen many questions come in exam. So now let's see resistivity versus temperature graph. So for copper, the value of temperature coefficient, we will talk about the temperature coefficient, is positive and very high, meaning that when you increase the temperature, the resistivity of copper will increase sharply. As you can see, when the temperature is increased, the resistivity increase very sharp. So that's why I call it copper has positive and high value of temperature coefficient, that alpha is very high for this copper. So with temperature, its resistivity changes rapidly. So this is for copper. So same thing again. So for alloys, so alloy also have the positive. As you can see, with positive means the temperature resistivity increases with the temperature. So it has positive but small value. As you can see, the change is not more, so it is almost constant in the graph. So that's why these alloys are used to make a heating coil, because when the temperature increases, its resistance do not change. If the resistance change, then current flowing through the wire will be less and the heat produced will be less. But in this case, the resistance or resistivity will not change, so it will keep on giving the same amount of heat. So its resistivity do not change rapidly with temperature as in conductor. So that's why alloys are good for making heating coil, because their resistivity do not change much with the temperature. So it has positive but small. In the copper it was positive but it was high value of alpha, so value of alpha is less. So but for semiconductor and carbon, they are negative. So negative means with increase in temperature, resistivity decreases. As you can see, in previous case it was going up because of the positive value of alpha. Now the semiconductor, their resistivity or resistance decreases with temperature, so they have negative values. So that's why it decreases with increasing temperature. So ohmic conductor, as we all know, they obey Ohm's law, and V is proportional to I. So that's why we get the straight line passing through the origin. So this is for metals and electrolytes, they are ohmic conductors. So for non-ohmic conductors, just the opposite of ohmic. So they don't obey Ohm's law, and V is not proportional to I, and VI graph is not a straight line. So, and examples are metals also, they don't follow Ohm's law when the current is very high. So we'll discuss it later. PN junction diode, thyristor and gallium arsenide, these are the semiconductors. So let's see the graph one by one. So see, metals, when the current is very high, so when the more current flows through the conductor, it produces heat, due to which resistance increases, and the V, which is V is equal to IR. If the resistance increases, voltage increases non-linearly. All of a sudden voltage increase, because due to the heat, the resistance increases. So metals also don't follow Ohm's law when the current is very high. So this is VI character of a PN junction diode. This side some part is linear, but as you can see, they are not, current and voltage, they are not increasing linearly. First voltage is increasing, current is not increasing, all of a sudden it's at, and at the negative side, when the voltage is increased in opposite direction, so current, after some time current start increasing all of a sudden. So they don't follow Ohm's law. And this is thyristor. So for the same voltage in this region, we will get the two values of current, and this is also not a straight line, so they are also not following the Ohm's law. And this is gallium arsenide. So this is a semiconductor in which, see, the voltage and current increases, but after some time current will start decreasing with the voltage. So this reason I call it negative resistance, because when you increase the voltage current decreases. So this is the negative reason. So gallium arsenide is also non-ohmic. I think this is the end of video. Thank you.